Hello, I'm Yannick Christiaans from UGent Campus Kortrijk, and I'm part of the Design Nexus research group. I teach at the Bachelor and Master of Science in Industrial Design and Engineering Technology at the campus, and I specialize in product design and prototyping. Our research group, Design Nexus, um, implements design strategies and best practices together with industry and organizations from both public and private sectors, and our focus is on education, sustainability, and industry. We have a strong partnership with MICT EMEC, who focuses on user-centered design, smart products, ISYE and Flanders Make, who is at the forefront of Industry 4.0, and CPMT, who are specializing in polymer processing and also 3D printing technologies. In this webinar, I will talk more about interesting business cases and applications of 3D printing, as this is where we specialize, as this is one of our specializations at Design Nexus. So we do not develop 3D printing technologies nor materials. We do try to use additive manufacturing in a meaningful and innovative way so it can contribute to more sustainable product design. So, just to start, I want to point out that additive manufacturing is at its best when we are trying to manufacture complex structures. For example, ready assembled parts, parts with internal features that cannot be accessed by conventional tools. Think, for example, of the milling head of a CNC machine, or if we are trying to make metamaterial structures. So you see the little chair on the bottom, which was a design by Materialize, which comes ready out of the machine, pre-assembled. In the middle, a drawing of soluble support in a very complex structure, and then on the other side, the very complex lattice structure used in the soles of those sports sneakers. So, for complex structures, when you would like to apply them with polymer additive manufacturing technologies, I would advise to either use FDM, which allows you to print multiple materials. So you can use one material which is soluble in water, a jetted polymer technology, for example polyjet, where the support can easily be removed using high pressured water, for example. Of course, the powder-based technologies like selective laser sintering, there the loose powder just supports the overhangs and you can just blow it away with pressurized air, or SLA technology, so photopolymers which are cured with a laser. There I do have to say that it's mainly the supports on the outside of the parts which are easily removed. Internal support structures are a little bit more complex. So now I would like to say a little bit more about long-lasting product design and additive manufacturing, as we feel that both go hand in hand. So long-lasting product design, this is something where we have to strive for globally. We have to move away from a consumer society where we discard products very easily, and then on the other hand we have design for additive manufacturing. When you look at the guidelines of both domains, you will see that there is quite some overlap. For example, the ability to easily repair parts is very much facilitated by design for additive manufacturing, since we can produce just in time without a lot of waste. The adaptability and upgrading comes also at a very low cost when using additive manufacturing, and so on. So now we move over to the examples. First of all, I would like to say something more about the metamaterial structures. So metamaterial structures are very unique structures where we design, let's say, materials which behave differently than when you would normally find them in their natural behavior. Take, for example, the door handle you see. This is built up out of a flexible filament. So normally flexible filament, it stretches and then it returns to its original shape. In this example by the HPI in Potsdam, they designed special structures which can compress and stretch in an engineered way. By doing so, they redesigned a complex assembly of many mechanical parts used for a door handle to one 3D printed part, which functions very well, as you will see. And if something breaks, you can just recycle the plastic and print a new part. A few other examples. Here you see an IKEA lamp, a topic which we tackled during a master thesis at the industrial design program of UGent. So we took an IKEA lamp, we analyzed all the forces in the lamp, and we tried to find ways to replace the mechanical joints by 3D printed parts. And this ended up functioning very well, although I have to point out that the side stiffness of the product is still open for improvement. Another example is a drum pedal. With my laser pointer, I am showing you the conventional drum pedal. Next to it, you see a similar drum pedal, but the chain, the rotation points, and a few other attachment points are replaced by one 3D printed part, where the hinges are replaced by metamaterial structures. This has a great advantage that the piece can be customized according to the drummer's personal preference, according to the feedback he or she desires from the drum pedal, and if something breaks, a spare part is very easily, very quickly made in a low-cost manner. Next, another inspiring example of the use of additive manufacturing we can find in customization. So just to start with, customization and personalization are two different things. It's a nuance. Nonetheless, personalization is very common with conventionally manufactured goods, where you have a predefined set of options where you can choose from, for example, different colors, simple parts which you can change and compose a new product. Think of shoes which can be customized online. Customization, on the other hand, goes beyond. There you can really tune a product to your very own preference. So we make one-of-a-kind products which are fully adapted to your preference in terms of aesthetics or ergonomical anthropometric preferences. Think about custom medical aids and so on. A few examples. This is a scissor to work in the garden. Normally this is made out of metal and injection molded parts. When the spring pops out of the scissors, which appears to happen quite a lot, this is a spare part which cannot be bought separately, so that's one problem. On the other hand, our student found out that these scissors are often difficult to handle for people with arthritis. So what did he come up with? With a series of 3D printed flexible springs, which can be assembled into a 3D printed handle. So both the spring and the handle can be fully customized according to the preference of the user, be it the hands of people with arthritis, kids who want to help their parents out in the garden and who might not have a lot of power to cut the branches, whatever. Next, customization can also take place in textile industry or in shoe manufacturing. Some of the leading brands in shoe manufacturing are really pushing this technology. We have done some tests with textiles where we try to, on one hand, repair textiles using 3D printing. So you will see here a fabric which is just put on the print bed of a conventional FDM printer. On the back we apply some paper tape, so the gap is closed, and then with a flexible filament we just cover up the gap. This is easily done on many of the printers which are available in fab labs or technical schools. On the other hand, we can also use 3D printing, FDM printing, to reinforce fabric. For example, if you are a person who has to work a lot on their knees, to prevent your work pants from getting damaged, you could print some protective structures on the fabric, so to prolong the lifetime of the product. Next up is an evolution we see in integrating electronics into products, and that's also where additive manufacturing can be very valuable, especially when we look at multi-material printing systems. There you use one nozzle with a conductive filament, or with an ink which is filled with silver particles, and you print it on top of a substrate. That way you can create sensors or switches. Think, for example, in situations where the electronic product might come in contact with fluids and you don't want any fluids penetrating the products. That's where integrated electronics can be very useful. And you see an example of a bionic eye which is being developed abroad. We also did some tests in-house several years ago with 3D printed electronics. Here you can see conductive filament, which is integrated into a dome, so a dual extrusion print head, and we have sort of a capacitive sensor, so when you slide your hands over the black parts of the lamp, you can adjust both the color of the lamp and the intensity. So those are things normally if you would have to do that the conventional way, the assembly would be way more complex. You would need a lot more parts you might have to source from abroad. Now you can integrate everything in one product, and on top of that it's waterproof, it's safe, for example, for outdoor applications. Next, we believe that 3D printing can be very useful in terms of spare parts. So normally when you need spare parts, I think, for example, when your coffee machine breaks down, very few people think of repairing consumer products because the spare parts are simply way too expensive. This is due to the fact that spare parts have to be stocked, they have to be shipped, making it a very expensive operation. If we were to make a transition to 3D printed spare parts, we can just produce them wherever we need them and very close to the end consumer. We see a transition in industry towards this practice. Several manufacturers of household electronics are already offering 3D printed spare parts. And where you see the image you see there is an example of a lighting module for big sports stadiums where they already print the spare parts. Next, another example could be football shoes. So this is one manufacturer who already 3D prints the soles of the cleats of their sports shoes with SLS technology. Unfortunately, it's still not possible in this specific case to replace the studs if they break off, but that could be a challenge for future designers and shouldn't be too complex to do. Another thing is that 3D printing can be used for tooling. So very often we look at additive manufacturing, 3D printing as a way to make end products, but in some cases 3D printing just won't do because the process takes too long, because the materials are not available, or we need a certain volume or a batch to be produced, which is just not economically viable with additive manufacturing. So in that case, we can also produce the tooling. Tooling for injection molding, as you can see on the image here. So these are SLA printed molds. We did this on a small desktop SLA printer, and we then injected thermoplastic urethane into the cavities with a small benchtop injection molder. Next, you see another SLA printed injection mold. So this was part of a robot of Ono, which is a robot, an open source robot, which is made for small children with autism. The eyes of the robot module were normally 3D printed, but this took quite a long time, and the result was not always satisfying, so we decided to give it a go and 3D print the molds and injection mold the eyes in polypropylene. So a polypropylene eye takes about, let's say 30 seconds to injection mold, and then we have to let it cool, but that's still a lot faster than when we would print it, and the finish is a lot better. So this is the best of both worlds combined. Also, you could use 3D print a mold to cast resins in, for example, silicones, urethanes, or to vacuum form something in. So you heat a sheet of plastic and then you vacuum form it over your mold. For example, if you would try to make samples of packaging or molds to cast chocolate or whatever. Then I would like to explain something more about modeling, so computer modeling and additive manufacturing. So it is our opinion that conventional CAD modeling you can already do a lot when it comes to additive manufacturing, 3D printing, but you really get the most out of the technology, as I explained earlier, when you make very complex shapes, and that is where CAD modeling software like Rhino and Grasshopper, which is a visual programming language, comes to play. So here you can see a very complex vase, which is actually completely built out of an algorithm. So nothing is modeled in CAD, it's just a script which is written, and that script generates that specific shape. The advantage is that it's very parametric, so you can very easily change it. It can quickly adapt, and it really uses the strength of additive manufacturing in terms of producing shapes. On the next slide, you will see a very rough example of a code. So you see a lot of nodes which each have a specific function, and that code then results in the chess piece you see here. So this is an algorithmically designed chess set, which is then FDM printed. So to model something like that in a conventional way would be very time consuming and maybe not even possible. With algorithmic design, we can do such a thing, and then really use the strength of additive manufacturing to produce such a thing. So with this, I actually want to conclude my story. I hope you had some interesting new ideas when it comes to additive manufacturing, and we look forward to hearing from you in case you would have questions.